All right, so we just got through endowing period spaces, moduli spaces of Hodge structures with a natural structure of a definable complex manifold. You know, we're sort of seeing that the best way to sort of, or at least I'm claiming the best way to sort of pick out, you know, how to say, just to recap, you know, it's enough to find a semi-algebraic fundamental set for the action of GZ. And I'm claiming that this is provided for by the sort of reduction theory of the Hodge form. And we saw sort of in the case of the modular curve, we're sort of getting something that is at least comparable to the usual fundamental set, which is good. So that's great. Now notice, you know, for Riemann surfaces, when we sort of built a definable structure coming from the sort of uniformization, it ended up being the same as the definable structure coming from the algebraic structure. Now this is no longer going to be the case because, you know, in general, this guy does not have an algebraic structure. So now we're actually going to sort of start, you know, stepping into sort of the part of the definable world where, you know, things aren't algebraic. And that's really where sort of we get some mileage out of this theory, because the definable structure, you should view the structure of a definable complex manifold as kind of sitting in between an algebraic structure and a full-blown complex manifold structure. Sort of nicer than a complex manifold structure, but it's not quite as nice as an algebraic structure. And therefore it's useful if we're dealing with spaces that, you know, don't necessarily have algebraic structures. And it really says something about their geometry if they admit a definable complex manifold structure, as we'll see. So now let's talk about what definable maps between definable manifolds are. And again, there's no surprises in this definition. If I have two definable manifolds, X and Y, and I have some map between them, then we say it's definable if once I take some definable atlases of X and Y, then all the maps sort of on charts are definable. And the only way that makes sense is by sort of taking the pre-image of a chart on Y and intersected with a chart on X, and, you know, because that's the only place where I can, you know, that's the biggest domain, that's the biggest subset of Xi on which I land into Yj. And we just require that all of these maps are definable. Okay, and there's kind of a subtle but important point here, which is that this is both a requirement on this map as well as a requirement on this set, right? This set, this intersection, isn't necessarily anything. So implicitly, we're both requiring that those intersections are themselves definable, and that this map from that intersection to Yj is definable. Okay, and both of those are non-trivial. Okay, I'm just going to go straight to quoting this theorem now, which is that, you know, we have a natural definable structure now in this moduli space of pure polarized integral Hodge structures. On algebraic varieties, we have a natural definable manifold. On a smooth algebraic variety, we have a natural definable manifold structure. And for any pure polarized integral variation of Hodge structures, we have sort of an interesting, we have an associated analytic map from X to a D mod GZ, just given by the period map. And the theorem is that with respect to these definable structures, the period map associated to any pure polarized integral variation of Hodge structures is definable. again, this is all definable in Rnx. Okay. So this is kind of a souped up version of the vague statement that the sort of the functions that arise in Hodge theory are sort of definable. This is an even stronger version of that, as I'm about to say, sort of on the level of spaces. So I'm not going to prove this, but let me at least indicate sort of where the important part of the argument is happening. Okay, so we've already done a lot of the work in some sense of proving this theorem. We, put a definable structure on D mod G in the first place. And we also know that we can take a definable cover of X, which consists of taking bounded sectors in punctured polydiscs on X, okay? And we have seen, using the nilpotent orbit theorem, that if I take the period map on the universal cover, that the restrictions to these VIs are definable. Okay, we saw that again using the nilpotent orbit theorem, because these functions are always, some combination of exponentials of nilpotent matrices and some restricted analytic function. Okay, so what's left to show? Well, what's left to show, and this is the hard part, is that we need the image. So for each one of these lifts, we need to show that the image of phi tilde on VI is contained in a definable fundamental set. Okay, so you see, there's quite a bit of difference between this function being definable as a map from VI to D versus being a map from VI to how do I want to say this? This is sort of getting at, this is maybe the best way to say this, is sort of getting at the fact that these intersections, we need to also show that these are definable. Okay, and this is related to showing that these images can be contained in a single fundamental set. Okay, and that's highly non-trivial, because this is some, this image a priori is some random subset of D. Why should I be able to stick it in a single fundamental set, which, for the upper half plane, we've already seen is vaguely close to a bounded vertical strip. Okay, so this is the hard part. And given how we've understood what the fundamental set is for, giving the definable structure on D mod GZ, we can translate it into a statement about the asymptotic reducedness of the Hodge form. Okay, which is much more sort of amenable to techniques that exist in Hodge theory. So basically, this is equivalent. This sort of missing piece is equivalent to showing that on these VIs, you can find some basis and some constant A such that the Hodge form is A reduced with respect to this basis, possibly after further breaking up the VIs into a further definable cover. Okay, so that's the missing piece that needs to be argued in order to get this theorem.
Can I ask something about the theorem?
Yeah.
So the usual period map has the monodromy group appearing in the quotient, right? And the monodromy groups are not necessarily arithmetic, so they can be of infinite index, right? Does this cause any problem, or is this because it's not necessarily clear that you can divide out the whole lattice, right?
So I think what you're saying is, sometimes, so if you take gamma to be the sort of image of the monodromy.
Yes.
of the variation of Hodge structures, then this period map, in fact, factors through just modding out by the monodromy.
Yes.
But so this guy has a natural definable structure. This guy usually does not, because gamma could be some weird thing. I mean, you can already kind of imagine this for like the upper half plane. I mean, you can mod out the upper half plane by SL2Z, and you get some nice finite volume thing. If you start modding out by some potentially kind of sparse subgroup, you could get some infinite volume thing, and then that's not going to have a nice definable structure that interacts in the same way. I will say a couple things about this point. So first of all, these two maps aren't that different. For reasons I will say later, the difference between these two maps is just some sort of finite algebraic map. So in fact, there's not that much lost in considering one over the other. So in my opinion, it's sort of better to, I mean, how to say, if I mean, if you were talking about like families of abelian varieties, you could, similarly, you can either map to AG, the moduli space of abelian varieties, or you can map to sort of Siegel space modulo the image of the monodromy group. And like, this would be a completely weird thing to do in that context. So it's much more natural to map to the actual moduli space of Hodge structures. I don't know. Anyway, the point, I guess the answer to your question is no, it doesn't cause any problems. And like mapping to D mod gamma is, as far as sort of the actual behavior of the variation of Hodge structures is concerned, it's purely cosmetic. I mean, there's very small difference between these two maps. Okay, maybe I'll say some more about that point in a second after I say something else. So okay, so this is a theorem. It has an immediate, very nice consequence, which I want to talk about. And that is we immediately deduce as a corollary a hard theorem of Catani, Deligne, and Kaplan, which is the statement that if I have a variation of Hodge structures over a smooth complex algebraic variety X, then I can look at the locus of points in X for which the corresponding Hodge structure has a Hodge class of bounded degree. And that locus is in fact algebraic. And the proof in this context is basically just immediately by definable chow. So let me just, it's sort of two steps. The first step is that there's a locus. I assume we've talked, Matt, I assume we've talked about Hodge classes at some point today? Briefly, okay. I can, if people want, I can define, I'm just assuming that we know everything about Hodge classes, but I can sort of spend a little bit more time talking about, recalling what they are and defining them, if people want.
Yeah.
Sure. Okay, let me do that then. Yeah, sorry. If I were there, I would have seen what had been said in previous talks, and it would be much easier to calibrate what I should say. That's why I left so much space on this slide, though, just in case. Okay, great. So let's just recall that let's even talk about the geometric case. So if we have, let's suppose our variation of Hodge structure comes from a family of algebraic varieties. So the fiber above a particular point of X is, let's say, the kth cohomology of let's do it with Q coefficients of the fiber. And we know that the Hodge structure is given by the decomposition into sort of HPQ pieces over C, where P plus Q equals K. Okay. And I'm sure this was said at some point, but where does this come from? Well, this comes from viewing singular cohomology as sort of smooth de Rham cohomology, and then using the fact that any smooth de Rham cohomology class can be uniquely represented by a harmonic form, and that the PQ components of harmonic forms are also harmonic. And that's what gives this decomposition, because these are precisely the sort of pure PQ type harmonic forms. Okay, and that's the sort of classical way of viewing this decomposition. And what it means is that what it's meant to show is that sort of this Hodge decomposition is like a kind of hard thing to do manually. In other words, if you have a particular class in a particular cohomology class, for instance, if you have the Poincare dual of some, let me take that back. If you have some random cohomology class, it's kind of hard to say how it decomposes into PQ parts, because it involves implicitly sort of representing that cohomology class as a harmonic form, and then and then decomposing it. But there is sort of one case in which you can say something about this PQ decomposition, and that is if your cohomology class is Poincare dual to an algebraic subvariety. Okay, so one sort of class to take, you could take eta, if Z is inside of YX, let's say of codimension K, then the sort of Poincare dual of the fundamental class of Z is an element of HK. And it's an element of pure type, I'm sorry, H2K. And it's an element of pure KK type. It's an element of HKK. Okay, and why is that? Well, I mean, that's because the sort of, if I, how to say, I mean, by definition, if I integrate along YX sort of alpha wedge this Poincare dual, that's the same thing as integrating alpha along Z, okay? And so I'm integrating sort of 2K forms along Z. The only possible ones that could give me a non-zero answer is those of type KK, because otherwise I have too many holomorphic parts, or too many anti-holomorphic parts to be supported on Z. Okay. So that's sort of one case in which we actually know how this decomposition behaves. And so the important remark to make here is that the sort of Hodge conjecture sort of predicts that, in fact, any rational cohomology class which has pure balanced type, pure KK type, has to come from integration along algebraic subvarieties. Okay, so the Hodge conjecture basically says that any element of H2K Y comma Q intersect HK K Y arises in this way. Whoops. Sorry. Maybe it's safer. Arises in this way. Arises in this way. Okay, and so these are called Hodge classes, right? This is now something that is, I can define purely in the realm of abstract Hodge structures. It's any sort of rational class which is of pure balance type is called a Hodge class of that Hodge structure. Okay, so given a Hodge structure V on sort of some lattice VQ, a Hodge class is equal to something in the intersection of VQ and sort of the KK part. Let's say this is a weight 2K. Okay, and now if I have a polarized Hodge structure, then there's a quadratic form Q floating around, and by the degree of that Hodge class, I just mean its degree with respect to Q. Okay, so this degree is just equal to Q of alpha comma alpha. Okay, which again, because we know the this is either depending on the weight is either positive or negative for any Hodge class, right? Because of the definiteness of the Hodge form. Okay, cool, great. So now yeah.
Sorry, shouldn't that be over set over the integers if you want to bound the degree?
Yes, that's a good point. Yes, so blah 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 blah, which has an integral Hodge class. Integral. Yes, right. So these are the rational Hodge classes, and you can look at the ones that are actually, if you have an integral structure, you can look at the ones that are actually integral. And here I want to look at the integral ones. Yes, thank you. Okay, great. What is blah 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 blah. So let me let me do this. Let me get a new slide. So how does this how does the proof of this this corollary work? Let me just give a few remarks. So the point is that in D mod GZ, we can look at the locus, the sort of universal Hodge locus. Let's say degree D Hodge locus, which is just the set of Hodge structures admitting a degree D integral Hodge class. So the claim is that this is a definable complex analytic submanifold. Okay, and once we have this claim, then we're completely done, because then if we take the sort of inverse image of this universal Hodge locus under the period map, which sits inside X, then this is definable and complex analytic. Therefore, by definable Chow, it's algebraic. Okay, so this is sort of the virtue of this definable setup. We can, rather than trying to sort of argue that the functions cutting out this locus inside, once we pull back to X, are not too crazy, and therefore they actually define an algebraic subvariety of X, which is how the argument of Catani, Deline, and Kaplan works. We can first argue that the functions aren't too crazy in D mod G, which is much easier, because it's sort of independent of the weird geometry of the period map. And then we can pull back along the period map, which we know has some tame behavior, and therefore it preserves the sort of tameness of those functions, and we can conclude that it's algebraic inside X. Okay? And so running that argument requires some ability to say what it even means for these functions to be tame. on D mod GZ, and that's where the definable structure comes in. That's sort of telling you sort of that what functions have good asymptotics. Okay. And I won't go in too much detail about this claim, except to say that it's basically obvious once you sort of know a little bit more about how Hodge classes work. And basically, the key idea is that if I have a rational class, if I have alpha inside of VQ, then alpha is Hodge, which recall means that alpha is in sort of the KK part. Well, alpha is a real class, so this is just equivalent to alpha being in the sort of FK part of the Hodge filtration. Okay, and now the sort of the set of Hodge filtrations for which alpha is contained in FK is clearly an algebraic subvariety of the corresponding flag variety. So therefore, the sort of locus of Hodge structures for which alpha is Hodge is just D intersect sort of an algebraic subvariety of D check. Remember, D check was parameterizing Hodge filtrations. Okay, so like these, inside of D, the Hodge loci have a very simple geometry. There's sort of intersections down with sort of algebraic subvarieties of D check. And so in particular, they're clearly definable inside D. So once again, we have to be a little careful to make sure that they sort of interact with the definable fundamental set given by this sort of Ziegel set. But once again, I mean, this sort of algebraic subvariety is some sub-homogeneous space, and therefore it interacts well with the group theory. And so this locus also interacts well with the sort of definable fundamental set. Okay, so one shows that this sort of intersects the definable fundamental set. In a reasonable way. Okay. I mean that's a little imprecise. I mean, of course, it intersects a definable fundamental set in a reasonable way because the intersection of two definable sets is definable. What I mean by that is that the sort of enemy would be that this Hodge locus, when you sort of take the image in the quotient, could look kind of crazy. You want to how to say, you want this sort of Hodge locus to be stabilized by like a big subgroup of GZ is actually what, anyway, I don't want to get into the details of that. The important point is that this claim is sort of is very easy given the sort of geometry of the period domain as sort of a homogeneous space. Okay, great. That gives us this nice corollary via definable chow. Let me mention a few more things about what you can say about period maps. And here's this is related to the question that was asked about D mod gamma versus D mod GZ. Here's a theorem. You should sort of view this as kind of the dual to definable chow, which says that a definable complex analytic subvariety of an algebraic variety is algebraic. And this is saying that if you have an algebraic variety mapping to a definable complex manifold, then the image is algebraic. Sorry, mapping definably to a definable complex manifold, then the image is algebraic. And it's harder to prove than definable chow, but I don't really want to get into the proof. It basically the sort of key point is you have to sort of upgrade the whole definable complex analytic machinery to a reasonable machinery of definable coherent sheaves. But the corollary, which is interesting, is that, well, we're exactly in this situation, right? We have a definable complex manifold, which is non-algebraic, but we have algebraic varieties that map definably to it. And therefore, we can apply this theorem, and we get that the image of any period map is, in fact, an algebraic subvariety of D mod GZ. In fact, it's a quasi-projective algebraic variety. And moreover, and I didn't say this in the theorem, but if we call the image, say, Z, so Z sits inside of here, then the map from X to Z is a definable map between complex varieties, algebraic varieties, and is therefore algebraic itself because of definable chow, right? I mean, if you have any definable analytic map between algebraic things, by looking at its graph is a definable complex analytic sub of an algebraic thing, and therefore algebraic. So this is an algebraic map. So this is what I was saying before about the only difference between the map to D mod gamma versus D mod G as being some finite index thing, and that's because if we look at let me just make this point now, we have sort of DGZ, we have like D mod the monodromy, okay, and we can take X and we can look at the image down here, and we get this Z, okay, and we can look at the image in here, let's call it Z prime. Well, this is just a finite étale map. Oh, sorry, it's not a finite map. It's just this is a covering space. Okay, so this is some covering map, but we know that this map is algebraic. And therefore, this is a finite étale map. Okay, so the difference between Z prime and Z is just we're possibly going up a little bit by some cover. So there's not so much difference between the sort of image of X in D mod gamma and the image of X in D mod GZ. Okay, okay, so that finishes what I wanted to say about definability of period maps. Any questions about that? Okay, now I need to go off book because I have run out of slides. Let me see what the best way to do this is. Okay. So I want to spend the remaining time talking a little bit more about some other things you can prove that are potentially useful about these period integrals. Okay, so let's go back. Okay, so these were sort of, remember the sort of setup was that we had a smooth projective family. Okay, and we were saying that we get a we get sort of, by looking at the kth cohomology of the fibers, we get this this vector bundle with flat connection, namely the Gauss-Menin connection. I'll call that the sort of Durham cohomology of X over Y. And its algebraic structure is given by algebraic Durham cohomology. And we were saying that in particular, that means that whenever I have a relatively closed holomorphic K form or algebraic K form, so a relatively closed algebraic K-form. Then I can look at the corresponding algebraic section, which is just take the class of the, omega restricted to the corresponding fiber. And this is an algebraic section of this vector bundle. And I can look at its coefficients with respect to a flat basis, which is just the same as integrating along a topological cycle. And I get these functions, okay, and these period integrals. These are sort of functions, multi-valued functions from y to c, sort of multi-valued. These are period integrals. Okay, and a lot of what we've been discussing about period maps is sort of encoded in these period integrals. For instance, because the sort of flag variety coordinates for the Hodge structure itself are given by sort of ratios of these period integrals. Okay, so let me make some remarks about these period integrals. Sort of these period integrals determine the period map. And the best way to sort of see that is by looking at the case of a family of elliptic curves, in which case, so if x over y is a family of elliptic curves, and we're talking about sort of H1, well, an elliptic curve, its H1, as we all know, is two-dimensional. So we have these two cycles. So we have sort of two integrals we can take. We have one along sort of the first cycle and one along the second cycle. And the point I want to make is that let me maybe switch to, the point I want to make is that the sort of upper half plane coordinate for the Hodge structure is just given by the ratio, right? So this ratio is the coordinate in the upper half plane for the Hodge structure. Okay, so the period map is a particular way of sort of packaging this information of the period integrals, which is, is not lossless. I mean, by taking that ratio, we're sort of controlling for the fact that there's some choice in this form omega, but the sort of the period integrals contain strictly more information. Another point I want to make is that well, now that we're talking about Hodge theory, I said you can take a relatively closed algebraic K-form and get a sort of class in algebraic Durham cohomology. Well, that actually only gives you a certain type of class in algebraic Durham cohomology, because if you want all algebraic Durham cohomology, one way to think of it is by taking sort of classes of relatively closed meromorphic forms. Okay, so to get all classes of this, we should actually take classes excuse me, relatively closed meromorphic forms. And we know this classically from Riemann surfaces, right? I mean, the whole cohomology is represented by classes of meromorphic one forms with no residues, modulo exact meromorphic forms. And then the sort of part of algebraic Durham cohomology represented by the actual holomorphic one forms is nothing more than the first part of the Hodge filtration. And that's in fact a general fact. The Hodge filtration F dot is a filtration sort of by pole order. Okay. Okay, so that's good. So in fact, we can more generally, I mean, there's nothing stopping us from taking integrals of meromorphic forms. We'll still get definable functions by the same argument that we had before. They just might, end up having some poles arising somewhere. Okay, so by the same argument as before. These functions are definable for omega y, for omega now relatively closed meromorphic. Okay, and the the sort of topic I want to spend the last sort of few minutes discussing is that of the sort of transcendence properties of these functions. So we have all of these holomorphic functions. This is these sort of multi-valued holomorphic functions on the algebraic variety, which is the base of this variation of Hodge structures. You can view them as sort of solutions to Picard-Fuchs equations, as we've said. They're very transcendental functions. They're like often not going to be algebraic, but we can sort of ask the question, sort of how transcendental are they? Question. How transcendental are these functions? And the answer is depends a lot on the geometry of the family. And there are some sort of stupid reasons for which this is true, and then there are some less stupid reasons for this is true. All of which we can see sort of from the case of families of elliptic curves. So first of all, if we have a trivial family, then obviously these functions are all going to be constant. And we're not getting any transcendence. Okay, so the transcendence of these functions is certainly related to the family itself being non-trivial. But here, so that's the sort of first case. So if family is trivial, or if the corresponding variation of Hodge structures has some trivial pieces, then the corresponding periods will of course be constant. The family is trivial, or if variation has some trivial parts, then these functions will be constant, or rather they won't necessarily be constant, but they'll be algebraic functions on the base. Will be algebraic. Right, because we're putting in any meromorphic form here, so you could just multiply by an algebraic function on the base. Get that back. Okay. What about if we take if we do the following? So now let's consider taking two elliptic curves over, I don't know, some curve, let's say B, and let's consider the fiber product. So this is some family of a billion surfaces. Whoops. This is the two. Okay, and sort of what sort of periods we get? Well, obviously we get the sort of periods of the two families of elliptic curves. So we get the sort of I don't know, the alpha 1 omega 1 and the beta 1 omega 1, and we get the alpha 2 omega 2 and beta 2 omega 2. Okay. And if these two elliptic curves are isogynous, then that's going to imply some equality between these periods, right? So if E1 and E2 are isogynous, then there will be some dependence among these. Okay, so, of course, that's kind of clear from construction, but if we had just started with this family without knowing that it was a product of elliptic curves, or then, we're seeing some drop in the transcendence degree of the sort of field generated by these period functions that is secretly coming from some geometry that maybe we didn't know before going into it. Okay, so the punchline of these sort of very simple-minded examples is that these period integrals tend to be as transcendental as they should be, sort of given the geometry of the family. Or another way to put it, if there's an algebraic relation among these period integrals, then there should be some geometric explanation for it. And this is kind of a vague principle which has a precise formulation. So a vague sort of principle. So these period integrals should only satisfy algebraic relations sort of that come from geometry. Okay, and sort of giving some making this statement more precise is what I want to spend the rest of the time doing, because it turns out these sort of transcendence questions were the first entrance of these O-minimal methods into Hodge theory. So actually, you can get a lot of mileage out of these definability methods to prove statements about the transcendence of these functions, which is in some sense not surprising, because sort of we have these analytic functions. We want to say something about how they interact with the algebraic structure. And that's exactly what sort of definability does for us. And the other reason I want to say something about this is that this is really where the Pila-Wilke theorem that I mentioned last time, this sort of, we've seen a couple applications of definable Chow, but this sort of second algebraization theorem that I talked about last time, which was more arithmetic in flavor, we haven't really seen where that's used ever. And that really comes into its own in the sort of the world of transcendence of functions. Okay. So I'm not going to be able to say too much of this, but I at least want to formulate some precise statements. And to do so, let's go back to the complex exponential. Let's look at sort of e to the 2 pi I z. Let me just call it exp. And let's actually view it as a map from c to the n to c star to the n. So here I'm just exponentiating each factor. Okay, so now there's an old conjecture called the Shanuel conjecture, which is about the transcendence of actual numbers. And it says the following. Suppose alpha 1 through alpha n inside of C are Q linearly independent. Then the transcendence degree of the field generated over Q by these numbers and their exponentials, I'll put in the 2 pi I, because that's what we've been doing. But you don't need the 2 pi I, is bigger than or equal to n. This is the transcendence degree over Q. Okay. Now, this conjecture is still wide open, and it, in particular, sort of implies the transcendental independence of like E and pi. And this is sort of a hard conjecture. It's sort of hard to prove transcendence of like actual numbers. But it has a functional analog, which was proven by Axe in the 70s. So the functional analog is the following: functional analog. This is the sort of Axe-Shanuel theorem. Suppose F1 through Fn are formal power series complex power series, formal complex power series, which are Q linearly independent modulo constants. Then the transcendence degree of the field, so now this is over C, the field generated by these functions together with their exponentials is bigger than or equal to n, plus now we also include the rank of the Jacobian of the sort of formal function we get by putting the f's together. Okay, so let's pause for a second here, now that I have both of these written up. And let's go back and understand why I have this condition on being Q linearly independent. And that's because, well, if we're talking about transcendence degree, we're talking about sort of how algebraically independent things are, right? And what we're looking at the field generated by the alphas together with their exponentials. So we're kind of looking at both relations between the alpha i's and between their exponentials and between the alpha i's and their exponentials. Okay, so it's some kind of mixing of the sort of algebraic relations that might be satisfied just between the AIs and just between their exponentials. And the reason this Q linearly independent condition is there is because there's one kind of obvious algebraic relation involving that sort of mixes, the alphas and their exponentials. And that is if, for instance, alpha 2 is 2 times alpha 1, then the corresponding exponential will be the square of the other, right? So if like alpha 2 is 2 times alpha 1, then e to the 2 pi I alpha 2 is equal to e to the 2 pi I alpha 1 squared. Okay, and so that will be an example that will contradict this theorem if I just plug in some random alpha 1, because I have and take alpha 2 to be 2 times alpha 1, because this is sort of one kind of algebraic relation that taking exponentials respects. In other words, it's an algebraic relation which gets sent to another algebraic relation when we exponentiate. Okay, and for the same reason, we have the same condition down here, because you can also manufacture this sort of these algebraic relations between exponentials downstairs. What this theorem is really telling you is that the only way that algebraic relations among the alpha i's gets translated into algebraic relations among their exponentials is if it's an algebraic relation that looks like this. Okay. Okay, so far maybe this seems slightly removed from from what we've been talking about. When did I start, by the way?
I think 55 minutes ago.
Oh, 55 minutes ago. I see. Okay, I have less time than I thought I did. Okay, so let me just very quickly sort of explain how we sort of view this kind of statement more geometrically. Okay, so here's how we want to interpret this geometrically. So really, these FIs we should view as being a map from some ball into Cn. Okay, so they're formal power series, but we don't lose anything by considering convergent power series, in which case we have an actual map from the ball into Cn. Okay, and let's think about what this inequality is actually doing. Okay, what is the transcendence degree of this field? Okay, well, it's nothing more than if we consider, if we have F, which is a map from this ball to Cn, then in particular we have a map from the ball into Cn cross C star n, given by, well, it's F on the first coordinates and it's e to the F on the second ones, or e to the 2 pi I F. It doesn't really make a difference. So let's call this map G. Okay, so the functions we get, these functions here are exactly the coordinate functions of the image of this ball. Okay, so this transcendence degree is really just the dimension of the Zariski closure of this image. Right? I mean, that's what the transcendence degree is measuring. It's measuring sort of the number of algebraically independent elements of this field, and those are giving us sort of algebraically independent coordinates, and then it's just the dimension of the Zariski closure. Right? This field is precisely the function field of this Zariski closure. So what this equality is telling us is that the dimension of the Zariski closure is bigger than or equal to n plus, well, what is the rank of the Jacobian? It's nothing more than the dimension of this image itself. Okay, so here we're sort of comparing, we have this this parametrized analytic subvariety of Cn cross C star n, and we're sort of comparing its dimension we have this parametrized analytic subvariety of this particular type. In particular, it lands inside the graph of the exponential. And we're sort of comparing how big the Zariski closure is compared to the actual dimension. And we're saying that the Zariski closure must be at least n dimensions bigger, as long as this G of B is not contained in a subtorus. Okay, as long as G of B is not contained in a coset of a subtorus. Okay, so now finally we can interpret this sort of actionual version of a transcendence statement as an unlikely intersection statement, and that's as follows. Suppose we look at this product. Sitting inside of here, we have the graph of the exponential, which is this like super transcendental thing. Okay, let's take some random algebraic subvariety. Okay, so secretly this algebraic subvariety is in order to recover this previous form, we'll take just to be the Zariski closure. So what we're saying is that what is if we take W to be the Zariski closure, this image of this actual ball is going to be something close to the intersection of W with this graph. Okay, and let me just sort of fast forward to the end statement now, but you can sort of work this out for yourself. What we're really saying is that if U is a component of this intersection with unexpected codimension by which I mean, so the codimension, we would expect that the codimension of U inside gamma should be equal to the codimension of W inside of Cn cross C star n, right? Because, you know, that's the, we expect if we're intersecting with a codimension C subvariety, we expect codimension C. Sorry, if we expect the codimension, you know, to be the same when we cut it down. So if this intersection is larger, namely the codimension is smaller, then something special must be happening. So then U is contained in the graph gamma restricted to a coset of a subtorus. Okay, so now I'm sort of running out of time, but the point here is that this sort of statement about the transcendence of those functions we have rephrased in terms of saying something roughly like the following: if we have some algebraic variety in this product with which intersects the graph of this very transcendental function in a unexpected way, then it must be because of some geometry. Okay, and so this is exactly the kind of statement that generalizes to this sort of Hodge theoretic setting. Basically, I mean, now that we have this sort of geometric formulation, it carries completely over. So let me just say a couple things. So sort of Akshanual for period maps. We basically just replace, I mean, we have the exponential here. Where is it? We have the exponential here. We basically just want to replace the exponential with the map from D to D mod GZ. Okay. And so what we're saying is, suppose we have some, let's call this pi. Suppose we have an algebraic. So we have to be a little careful because there's no algebraic structure on this guy. But if we give ourselves a period map, then this has an algebraic structure. So now we can talk about inside X cross D. If we have some algebraic subvariety, and on the other hand, if we have sort of the graph of the period map, then here's the statement: if U is a component of this intersection of unexpected codimension, then U, and so here's the key part, then U is in the graph of phi restricted to a Hodge locus. Okay, sorry. So this is, it takes me a lot longer to write than I expected. Anyway, the point I'm trying to make is the, you know, for the exponential map, the extra geometry that accounted for sort of algebraic relations between the exponentials was being in a subtorus. In the context of period maps, the extra geometry that gives rise to more relations among the period integrals is the existence of extra Hodge classes. Okay, and I'm not, you know, making the statement so precise here, but the point I do want to make is that using these O-minimality techniques, you can actually prove statements of that form, namely that if you have, and you know, I was going to do an example, but I think I'm thoroughly out of time now. But you can prove statements of the form, you know, if you have more relations among period integrals than you expect, then it must be because of the existence of new Hodge classes. Okay, and so this is sort of an answer to this sort of question that I was asking. Can we show that sort of algebraic relations among period integrals come from geometry? And the answer is, well, we can at least do the sort of Hodge theory part of it. And then, of course, we need the Hodge conjecture to show that, those, Hodge classes actually come from algebraic set brackets. But anyway, okay, sorry, let me stop there.
Thank you. Well, it's pretty late, so.